Welcome back. Let us continue our discussion on the Carnot engine, where we saw that an ideal gas was employed as a working substance in a reversible cyclic heat engine, and we find that during one cycle of operation, there are two state functions that I have identified for which the change is equal to 0. The first one is obviously the change in internal energy, and the second quantity is Q reversible by T. So let us have a look at in a little more detail what it means. Now we already have computed the efficiency of a Carnot engine. So for any cyclic engine, since delta U is equal to 0, I can always say that the total magnitude of work done must be equal to the total magnitude of heat absorbed. Therefore, I must be having magnitude of W equal to magnitude of QH plus QC. Therefore, by definition, I find that eta is equal to 1 plus QC by QH. Now, as the Carnot engine works reversibly and employs an ideal gas, in that case, I can always write QH is equal to nRTH ln VB by VA. That is something that we have been working on in the previous slide. And we also know the magnitude of work done in terms of the temperature of the high temperature reservoir, temperature of the low temperature reservoir, and the volumes of the state points A and B. Now, if I put these back and try to write down the efficiency of the Carnot engine, what I find is all the terms like nR and ln VB by VA, they are going to be cancelled when I take the ratio, and I will be left with TH minus TC in the place of W and only TH in the place of QH. And therefore, if I rewrite the efficiency of Carnot engine, I say that eta is equal to 1 minus Tc by Th. So what's the difference between these two expressions? While this expression is valid for any cyclic engine, this expression is valid for a reversible cyclic engine that is exemplified by the Carnot engine. But for a Carnot engine, now I can equate these two quantities. So that is what I get over here. I write down right hand side from this equation here, and I put it equal to the right hand side of eta as I read from here, and then I rearrange the algebraically the expression, and this is what I get. So let us have a look at these terms that I have got here. So what is the first term? The first term talks about a ratio of isothermal heat absorption to the event of isothermal absorption of heat at temperature TH. So the quantity that we are calculating is QH, that is the amount of heat absorbed at that temperature TH divided by TH. If we look into the second quantity, we find that this corresponds to the isothermal release of heat at the cold temperature reservoir, whereby at the temperature Tc, Qc was the amount of heat exchanged. And for that event, I compute the ratio Qc by Tc. And for a reversible cyclic engine such as the Carnot engine, I find that this ratio plus this ratio is equal to 0. Now, here I explicitly introduce to you the term entropy. So, I would say that over one cycle of Carnot engine, I can definitely write down that dq reversible by T, this expression, when integrated over a cycle, that gives me QH by TH plus QC by TC equal to 0. Therefore, I can say that since any reversible cycle can be approximated by a series of Carnot cycles as shown in this figure, you would say that this quantity, that is the cyclic integral of dq reversible by T, must be equal to 0 along any reversible cyclic path. And therefore, I conclude that we now have at hand a state function called entropy, which is identified such that ds is dq reversible by T and it is an exact differential. And what is delta S? I have delta S as the final value of S minus the initial value of S during a change in state from A to B, and this is given by the value of this integral. Look at delta S. Its value depends only on the value of S in the final state and the value of S in the initial state. Therefore, the value of delta S is independent of the path. And therefore, I argue that we have looked into a state function now which is entropy, which is defined like this, where ds is an exact differential and delta S is independent of the path. So now what I can do is I can use these two as a key relationship and continue my search for a new system property that decides the direction and endpoint of a spontaneous process. So here is the new concept entropy, and this is a state function. So for an infinitesimal change in place, you have an exact differential ds, which corresponds to the ratio of two quantities. One is the infinitesimal amount of energy, thermal energy exchanged reversibly when the system undergoes this change in state, and this heat must be exchanged at the temperature T. If during a change in state there are several such exchanges of thermal energy, in that case what I will do is I'll add them all up, I will integrate them, and I'll get the delta S value. Now, key questions about entropy are as follows. We have identified entropy as an outcome of Carnot engine. But for any general process, is it possible to estimate the change in entropy? That is the very first question that we have in mind. Now, what is the use of this state function? Especially, we would like to understand if entropy is useful to predict the direction of spontaneous change in state of a system and the condition of equilibrium that the system will achieve when it is allowed to undergo a change in state. And finally, we would also like to understand what is the connection of entropy to explain why the heat engines do not have ideal efficiency. So why is it so that if I have a system having an internal energy U, and if I supply it with some heat Q, why wouldn't it be able to convert this entire amount of input energy in a cycle into doing useful external work? So let us first focus on the estimation of delta S for different processes. So to keep things simple, I will be assuming 1 mole of the substance in the rest of the examples that I show you here. So by definition, once again, ds is equal to dq reversible by t. Now if I have an adiabatic process, by definition, dq reversible is equal to 0. Therefore, for non-zero temperatures, I must be having ds is equal to 0. Now if I now integrate as the system passes from state 1 to state 2, I find that S2 minus S1, that should also be equal to 0. And therefore, if I have an adiabatic process, it immediately tells me that the entropy of the final state is equal to the entropy of the initial state. Let us take some more examples by keeping in mind these two key relationships. The first is, for any isothermal process, delta S can be simplified. Since delta S by definition is this, I can take the temperature, a constant in an isothermal process, out of this integration. Now what is this quantity? This quantity is nothing but the total amount of heat exchanged during the change in state as it passed from the initial state 1 to the final state 2 in a reversible fashion. So you must realize that here I have again and again emphasized the fact that the definition involves a reversible process. Now, if I have an isothermal expansion of an ideal gas, in that case, I will use the properties of the ideal gas. I know that if it is an isothermal expansion, for an ideal gas, delta U is equal to 0. Then what does the first law of thermodynamics tell me? In that case, I must be having Q reversible equal to minus W reversible. Now, what is W reversible for an isothermal expansion of an ideal gas? We have already learned how to write it down. So for 1 mole of this ideal gas, this is the expression. And therefore, I can very easily write that Q reversible by T would be RT ln V2 by V1 divided by T. And correspondingly, delta S is going to be given by R ln V2 by V1. If I look at an isocodic reversible process, in that case, since it is an isocodic process and we are considering pressure volume work only, the dW reversible is going to be equal to 0. And now du is dqv, which in general for 1 mole of the substance is Cv into dt. And therefore I can write delta S, which is this integral, that must be equal to Cv into dt by t integrated from the initial state 1 to the final state 2. Why is that so? That is because I have just taken this expression of dqv and put it here. And therefore, if I carry out this integration, the result is delta S in an isocodic reversible process is given by Cv ln T2 by T1. Now, if I have a reversible process that involves changes in temperature and volume both for 1 mole of an ideal gas, I can very easily write that dq reversible is equal to du plus pdv. Now this follows from the first law of thermodynamics. So what is dq reversible by t? I divide both sides by t and this is what I get. But I have, please remember, an ideal gas. Therefore, I can replace du by Cv dt, and therefore I find that the left hand side of this equation by definition is ds. And this now is equal to Cv by T dt plus R by V dV. And therefore, this is the infinitesimal change in the entropy of the system when its initial equilibrium state given by T and V for a closed system has gone to a final equilibrium state whereby its temperature has become T plus dt and V plus dV such that S has become S plus ds. It is expected that ds would depend on dt and dv, and this is how ds depends on dt and dv. If I now integrate between two states, the initial and the final states, I will get delta S, that is equal to Cv into this integral plus R into this integral, and therefore the final result is going to be Cv ln T2 by T1 plus R ln V2 by V1. As you can very easily see, if I have an isothermal process, the first term vanishes, you are left only with the second term. If I have an isochoric process, then this term vanishes and we are left with the first term only. Now, to continue our discussion, then let me say till now I have talked only about reversible processes. And now you know that if a system passes from this initial equilibrium state to this final equilibrium state, you know how to calculate the delta S. So delta S is given by an expression like this. Now, if I want to carry out the change in state between the same pair of initial and final equilibrium states, but this time I carry out in an irreversible manner, my question is, what will be the delta S value? Of course, the delta S value is going to be the same. Why is that so? That is because delta S is equal to S2 minus S1, value of entropy in the final equilibrium state and value of entropy in the initial equilibrium state. So as long as we are going from the same set of initial and the final equilibrium states, it doesn't matter if I take a reversible path or an irreversible path between them, I should get the same result. Therefore, this is a very important observation as far as estimation of change in entropy is concerned. And this is exactly what has been highlighted over here. Now, let us think about a little more complicated situation. I'm thinking about reversible heating at constant pressure, where once again the same definitions of ds and delta S are valid. So, if I am doing a reversible heating at constant pressure, I know that dq reversible, that is dqp, must be equal to Cp dt. We have studied this before. For 1 mole of the substance, then what is going to be delta S? All you will have to do is divide dq reversible by T on this side. So, the right hand side becomes Cp dt by T. If I now integrate these two, so this is dqp by T, and if I now integrate from the initial state to the final state, the result is delta S, that is delta S is this integral. So, instead of this integral, I write delta S, and the result is Cp integral dt by T between T1 and T2. So, delta S is Cp ln T2 by T1. Now, if I have a reversible heating at constant pressure, there is a possibility that the system might undergo a change in phase. For example, if you are heating solid ice at 0 degree centigrade and 1 atmospheric pressure, and under that condition there will be a phase transition whereby the liquid water, the solid ice will take the heat as its latent heat and melt into liquid water. So, during reversible heating at constant pressure, there can be a phase change. So the first case that I have mentioned here, this is the situation where there is no phase change. But indeed, there can be a phase change as well when you are carrying out reversible heating at constant pressure. Under such condition, you must realize that while you are supplying the latent heat, the entire amount of heat is used up to convert the solid phase into the liquid phase, and the temperature remains constant as long as this phase transition is taking place. And therefore, under such condition, as temperature remains constant, I can take the T out of this integration. So once again, delta S turns out to be Q rev by T. So what is Q rev? That is the total amount of heat exchanged during this reversible heating at constant pressure. And therefore, this must be equal to the change in enthalpy during the phase transition. Therefore, delta S is given by delta H for the phase transition divided by the temperature at which the transition is taking place. Now, here is a summary of all that I have talked about for the determination of delta S for many different processes that we have talked. So, of course, if you are solving some problem, this is the summary that you need to consider. And you also understand that, well, if I know which formula to use in which situation, you can always get a quantitative estimate of delta S. But it's very important to understand that just memorizing these formulae is not good enough. You have to know why in certain cases there are two terms, why in certain cases there is only one term, and why in other cases delta S is equal to 0. And for that, you must understand the process that is involved in doing the experiment. And so far, I have always said that ds is defined as dq reversible by t, and I confined my attention to reversible changes in state. So, is it possible to estimate entropy change in a reversible process? Sounds ominous, isn't it? But we have already seen one example which says that if I know the initial state and if I know the final state, then the change in entropy is going to be the same irrespective of whether I take the reversible route or an irreversible route. So let us take some example that we will come across again and again in real life. So take this example of isothermal irreversible expansion. Here, the initial equilibrium state was characterized by a temperature T, volume Vi of the ideal gas, and the number of particles N for the ideal gas. When I go to the final equilibrium state, when the gas has filled up the entire box, the final equilibrium state is the same temperature T, but now the volume has changed to Vf, that is the final volume, and the total number of particles is the same. So once I have identified the initial equilibrium state to the final equilibrium state, I would like to know the change in entropy as I go from this state to this state. And this I can do very easily if I can think of an isothermal reversible expansion that takes the system from this initial state to the final state. So here the only thing that changed is the volume under isothermal condition, and therefore I can immediately write for 1 mole of this ideal gas, delta S is going to be R ln V final by V initial. Is that clear? Okay. So next, it may not always be possible to construct a single such experiment for a given irreversible process between a given pair of initial and final equilibrium states. One such example is freezing of supercooled water, and another example is the mixing of two ideal gases. Now, if you take water and rapidly cool it at a given pressure, you can get supercooled water even at a temperature of minus 10 degrees centigrade and 1 atmospheric pressure. But if you just even touch the vessel containing this supercooled water, it irreversibly solidifies into the more stable phase that you expect here, which is ice. Now, as you see, the initial equilibrium state and the final equilibrium state, both of them are present at the same temperature and same pressure. So, what is different between these two states? These two states are different because in the initial state, I have a liquid water, and in the final state, I have solid ice. Now, if I want to find out the change delta S in this irreversible process, this is how we can do it. We can heat up the liquid water from minus 10 degrees centigrade to 0 degrees centigrade at constant pressure. So this is a thought experiment, not an actual one. And then you can allow the liquid water to freeze at 0 degrees centigrade and then allow it to cool down to minus 10 degrees centigrade. So what are the three steps that I have included in my thought experiment? The first one is a reversible heating at constant pressure, which will give you delta S1. The second step involves a reversible phase change at constant temperature and pressure. That will give you delta S2. And third step is the reversible cooling at constant pressure. Once again, you can find out what delta S3 is. And therefore, in the irreversible change in state from liquid water at minus 10 degrees centigrade at 1 atmosphere to solid ice, I can find out the delta S for this irreversible process as a sum of delta S1, delta S2 and delta S3. Another very important example is the entropy of mixing of two ideal gases. So here the initial step is I have the blue gas at a pressure P, temperature T and V1 volume of it containing N1 molecules. I also have another ideal gas, the red gas, which occupies the volume V2 and it has N2 molecules under the same condition of pressure P and temperature T. And if I now withdraw the separator between them without changing the total temperature, then what I will find is that they will spontaneously mix and I can adjust the final equilibrium condition such that in the final equilibrium state they are present at the same pressure P, same temperature T, but now my system contains N1 plus N2 number of molecules of the two gas and the volume occupied by my system is V1 plus V2. So this is an irreversible process. This is a mixing process and I ask the question how to find out the delta S for a process like this. In order to do this, I will devise two thought experiments where I will take each type of gas and allow it to expand isothermally from a volume V1 to a volume V1 plus V2. So under such condition, what is going to be the change in entropy for my gas 1, which is colored in blue? That will be given like this. And corresponding change in the entropy of the red gas, gas 2, is going to be given by this. Usually for mixing, delta S mixing in this case will be given by delta S1 plus delta S2. Now, it is actually easier if we just note down that these are ideal gases, and I can play around with a simpler form of the ratio of the initial volume and the final volume, and I can write them in terms of the mole fractions of the two components. If I do that, in that case, what I will find is delta S1 is related to X1, that is the mole fraction of the blue gas, gas 1 in the mixture, and S2 is a function of X2, that is the mole fraction of the red gas labeled as gas 2. So, delta S mixing is now given in terms of N1R ln X1 and N2R ln X2. So, by definition, I have X1 plus X2 equal to 1, and also I would write that N1 plus N2 is some kind of total value of N. Now, if I divide both the terms by N, I will have to multiply by N on outside, and this will make this expression look like this. So, now I have this situation that for the irreversible mixing of two ideal gases, I can indeed find out the delta S of mixing in terms of the mole fraction of each of the components present in the final equilibrium mixture. So, what we have learned in this set of lecture is that entropy is a concept that emerged from the construction of a heat engine, the reversible cyclic heat engine known as the Carnot cycle. But entropy is a perfectly general idea. It is a state function. It can be computed if I know for a given change in state what is the amount of heat exchanged reversibly at a given temperature. And once we know the concept of entropy, then we can compute the change in entropy for a wide variety of systems, which may involve heating, which may involve change in volume, which may involve change in pressure, which may or may not involve a phase change. And this gives us a very good idea about evaluating entropy at any temperature. So, for this purpose, let us consider heating up a solid, and then it becomes hotter, and then it goes into a liquid at a temperature Tf, and then we continue heating this liquid till at a temperature Tb it starts evaporating, turns into a gas, and therefore the entire experiment involves heating from the absolute zero temperature to any finite temperature T, such that the system has undergone a continuous change in state from solid to liquid to gas, and in the end we get a heated gas. So, for this process, one can very easily write down this expression where S of t minus S of 0 gives you the change in entropy of the entire process. Therefore, what is the entropy of the system at a temperature T? That must be S of 0 plus whatever change it has undergone. Now, each of these quantities that are required, like the specific heat of the solid, delta H of fusion, then the specific heat of the liquid and the gas, and the change in enthalpy, the enthalpy of vaporization, these are usually available in the literature. We can also use the known experimental results, such as the Debye law, which says that for a solid at low temperature, it goes as T cubed, and therefore put this expression back in here and carry out this integration and evaluate that particular integration for a given value of A. Similarly, we can use Troughton's rule to find out the delta H vaporization under standard condition. So, once we can do that, it is possible to measure entropy at any temperature provided we know S of 0. So in my next lecture, I will introduce to you the third law of thermodynamics, whereby you can find out entropy at 0 temperature. Thank you.